All right, y'all. Today we're going to be talking about graphing advanced rational functions. So last class we talked about graphing rational functions with transformations in our form with our a, our b, our c, and our d value. But that's not all the rational functions we could run into. We could run into rational functions given to us in standard form and even in factored form, kind of similar to some of our other functions that can be seen in multiple forms. And if we see in these other forms, we can still graph them. We don't have to exclusively have them in transformation form. So the first thing I want you to do is I want you to look through this top question here. And I've given you the standard form of f of x and the factored form of f of x, as well as a graph. And I want you to fill in those key features there on the right. We've talked about most of those already. Um, and then think of, um, yes, you can clearly see them on the graph, but using the graph, using the standard form, and using the factored form, how could you find some of that information maybe if you didn't have a graph? So if I took that graph away, could you find all of our key features just from the equation? So go ahead and pause me and think about that for a little bit, and then we'll go over it. All right, y'all. So hopefully you have some of those key features filled in. If you got all of them, fantastic. If you just got some of them, that's okay too. Go ahead and fill in the ones that you don't have yet. Okay. So our x-intercept and our y-intercept are pretty straightforward. We can see them clearly on our graph. Our whole, that's a new key feature to us, but hopefully you kind of picked up on that one point being an open circle essentially as opposed to that closed in dot, which that is representing our whole at 2 comma 3 fifths. And then our asymptotes, they're not clearly denoted on this graph, but looking at how our functions are going, I would say they definitely fall at x equals -3 and y equals 1. And then, of course, our domain and range, all real numbers except x does not equal -3 or 2. So important to note that for our domain, we exclude not just the vertical asymptote, but we also would exclude any holes that we have. And then our range, all real numbers except y does not equal 1, which is that horizontal asymptote like we've been used to. Okay, now let's talk a little bit about where some of these points can come from. So this x-intercept right here, -1 comma 0, I want you to note that there's a factor in the top of um, our factored form of x plus 1. Okay, so any factors that we have left over in our factored form um, are where we would get x-intercepts. Our y-intercepts, we've talked about this before. It's where we would plug in 0 for x. So plugging in 0 for x, we would just simplify the function down, and we would end up getting that value 1/3. Our whole, I want you to notice this x value of the whole is at 2. If you can see in our factored form, we have this x minus 2 over x minus 2. Now, if I have x minus 2 divided by x minus 2, those are the same things. They will cancel out. And when they cancel out, they're going to be equal to 1. And they'll change the way our function looks. And that's what creates that whole. When we cancel out that factor, it adds in that whole for us. So that's where that 2 comes from. And then we can take that 2 and plug it back in, and we'll get that 3 fifths. Then our vertical asymptote and horizontal asymptote, we've talked about these before with transformation form. They're very similar, just a little bit different. So our vertical asymptote, just like with transformation form, it comes from factors in the denominator. So that x plus 3 would still be there. So that gives us x equals -3 as a vertical asymptote. Our horizontal asymptote is a little bit wonky, and I'm going to teach you a way to remember this. But our y equals 1 actually comes from the fact that this is an x squared over x squared. So we divide the coefficient in front of it, which is 1x squared and 1x squared. 1 over 1 would give us 1. And then, of course, our domain and range, we just exclude any of those discontinuities like asymptotes or a whole. Okay, so super important to kind of keep in mind, super important to think about. And let's kind of put all of this, all that information that we just talked about is all down here below for our zeros, our y-intercept, for our whole, our vertical and horizontal asymptotes. I'm not going to go over all of them again. I'm going to give you some time if you need to. You can pause the video and copy some of this information down. A lot of this is just going to make a lot more sense when we do some problems together. But the one that I am going to focus in on is this horizontal asymptote procedure, because this is really kind of new and weird. It's really straightforward, but you do just have to remember the 3 cases, and there are 3 different ones. So the first case is that if the highest power of x is in the denominator, so that means whatever is in the bottom has a higher exponent than whatever is in the top, then our horizontal asymptote is going to end up equaling 0. So it will just be y equals 0. It will always be y equals 0 if the exponent in the bottom is larger. Okay. And this BOBO right here stands for bigger on bottom. So just like our bigger exponent being in the denominator, the bottom of the fraction, 0. So BOBO is a nice way to remember that if it's bigger on bottom, the horizontal asymptote is 0. Okay. Then the other way around, if the highest power of x is in the numerator, then there's actually no horizontal asymptote. So switch it around. If we have a higher exponent in the numerator in the top of the fraction instead of in the bottom, then we're not going to have any horizontal asymptote at all. We actually have what is called a slant asymptote occur. We're not going to really work on or look into those this year. You'll do that later on in math. But for today and for this year, we're just going to know that if it is bigger on top, then there's going to be none. There's no horizontal asymptote. And that's what that bottom stands for. Bigger on top, none. And then last but not least, and this is the one that we saw in our example, if the highest power of x is the same in both the numerator and the denominator, then the horizontal asymptote will be the coefficients divided. So we say exponents are the same, we divide the coefficients. So as an example, if I had 2x squared over 3x squared, my horizontal asymptote would be y equals 2/3. Okay. So you'll hear me say in class, Bobo button eats DC. That's kind of a nice mnemonic way to remember all of these. So bigger on bottom, y is equal to 0. Bigger on top, there is no horizontal asymptote, and exponents are the same. We divide the coefficients. Okay. So let's look at an example because this is kind of a lot of information you've been thrown right at the start of class. So let's actually do an example together, and I think it's going to start making a lot more sense. Okay, so we're going to look at A. We have f of x is equal to x minus 2 divided by x plus 5. And we're going to be finding all of that different information that we talked about. Okay, so first and foremost, and we didn't state this in our steps, but anytime we are graphing a rational function, the first thing we want to do is we want to check if we can factor. So x minus 2 over x plus 5, we don't have any greatest common factor we could take out of either of those factors. We don't have any factoring. We can split them apart. They are just a single x and a single x. So this is already fully factored. So I'm good to go ahead and find the rest of my key information. Okay, so first and foremost, we're going to do vertical asymptotes from our steps up above. Vertical asymptotes come from any factors that are in the denominator. So the only factor I have in my denominator is that x plus 5. So I'm going to take that x plus 5, and I'm going to set it equal to 0. Solving for x, we would get x is equal to negative 5. So my only vertical asymptote for this rational function would be x equals negative 5. For our horizontal asymptotes, we do that Bobo, Botten, eats DC. So we look at our two leading x's. Leading, remember, doesn't necessarily mean first. Leading means highest power, but we only have the x's, so they are our highest power. X over x, those exponents are the same. They're both an x to the first and an x to the first. So because those exponents are the same, we're going to divide those coefficients. So y is going to be equal to, and remember when I say divide coefficients, I'm not dividing the exponents, I'm dividing the numbers in front. And in front of these x's are 1 and 1. So y is equal to 1 over 1, which means our horizontal asymptote is just y equals 1. Okay, so hopefully pretty straightforward so far. The nice thing about this, yes, it's a lot of different information to find, but each one has a very specific process and step to follow to find it. Okay, so our next one up is our x-intercepts. So x-intercepts come from factors in the numerator. We only have a single factor in the numerator, that x minus 2. So I'm going to set that x minus 2 equal to 0. And that would give me x is equal to 2. But we're not going to write it as x equals 2. We're going to write it as an actual intercept, which would be 2, 0. Okay. So asymptotes are equations. X-intercepts, y-intercepts are points, so it's important to make sure we write them correctly. Okay, next up is our y-intercept, and just like our x-intercept we find from setting y equal to 0, our y-intercept we find from setting x equal to 0. So if x is 0, we can plug that straight into our function, so 0 minus 2 over 0 plus 5, negative 2 over 5. That's not going to simplify at all, so we can just simplify this to 0 comma negative 2/5 for our y-intercept. Okay, now next up is our whole. Did we have any factors when we were in our simplifying process at the beginning cancel out? We did not have any factors cancel out, so we are not going to have a whole. So an important thing to remember with rational functions is not all rational functions are going to have that whole. We only have that whole occur when we have a factor that cancels out. We didn't cancel out any factors, so we don't have a whole on this one. And then our domain, I'm going to do interval notation on this one. So let's do negative infinity to my only discontinuity in the x direction, which is that negative 5, in union with negative 5 to infinity. And then our range, same thing, but I'm going to split it that horizontal asymptote. So negative infinity to 1, in union with 1 to infinity. And that's really all there is to it, y'all. Okay, so we've found all the things. Now we just need to add them onto our graph. So our horizontal asymptote is at y equals 1. Our vertical asymptote is at x equals negative 5. Then our x-intercept is at 2, 0. Our y-intercept is at 0, negative 2/5. And we don't have a whole, so we can't add that onto our graph. But looking at our graph, see how we have these 2 points down in this bottom right kind of section of our rational function? That's going to end up creating one of our 2 rational curves. So we have that rational curve that's down there in the bottom right. Okay. Now, for our other one, typically, if this is a standard rational function, it always has that symmetrical shape to it. So if this is a true and standard rational function, we should have a curve that is that opposite, that diagonal, symmetrical to my other rational curve. Okay. But if you're ever unsure, A, or B, if you want to make sure to check, we can always plug a point in to see if that rational curve is going to be up here above my horizontal asymptote or down below my horizontal asymptote. So a point I can plug in, I want to pick a point just to the left of my vertical asymptote. So I'm going to pick this negative 6 right here. So we're finding our function evaluated at negative 6. So negative 6 minus 2 over negative 6 plus 5. Negative 6 minus 2 is negative 8 over negative 6 plus 5 is negative 1, which would give me 8. So that means I have the point negative 6, 8 on my graph. So I'm just going to plot that one for us. And just like we assumed, if I have a point up there in that section of my rational function, then that means that my curve would be up there as well. Okay. So in general, as we saw last class with our transformations, if it is a standard rational function, we should have that opposite curve behavior. But every once in a while, we won't. All right, y'all. So we're going to skip B for just a second, and we're going to go ahead and look at C. I'm going to see how much you can do on your own on this one. So first and foremost, I'm going to make sure we're all set up and ready to go. So on C, we have f of x is equal to 6x plus 12 over 3x minus 9. And just like we talked about last time, we always want to check first to see if there's any factoring or simplifying that we could do. Okay, so 6x plus 12 and 3x minus 9. Hopefully you're looking at that and you're like, oh, I could take some greatest common factors out. So for my top piece, for 6x plus 12, we could take 6 out of both of those terms. So that would give us 6 and leave behind x plus 2 over in the bottom 3x and negative 9. We could take a 3 out of both of those. And that would leave us with x minus 3. Okay. Now, simplifying a little bit further, x plus 2 and x minus 3, those are not going to cancel out. Those are different factors. But 6 over 3 we could reduce to be just 2. So we have 2, x plus 2, and then all over x minus 3. Okay, so we now have a simplified version of our rational function. One thing I do want you to note, yes, obviously our factoring and our simplifying here made it a little bit of a simpler rational function, but the real reason that we always factor is A, because all of those factors are what's going to give us our key features, and B, if we have like a whole or something that ends up canceling out, we're only going to see that if we do our factoring. So that's why it's so important to always factor first before we do anything else with our rational function. Okay, so I want you to go ahead and pause and just find the vertical asymptote and the horizontal asymptote for me. So just repeat the process for vertical asymptote and horizontal asymptote. All right, and hopefully you got x equals 3 and y equals 2 for your vertical asymptote and your horizontal asymptote. Just as a reminder, our vertical asymptotes come from any factors left in the denominator. The only factor we have left in the denominator is x minus 3, so we set equal to 0, and we get x equals 3. Our horizontal asymptote, we do that Bobo-Botten eats DC. In this case, 6x over 3x. Those are our two leading terms. They have the same exponent of 1, so we would divide those coefficients. So 6 divided by 3 would give us y equals 2. Okay, now that we found our vertical asymptote and our horizontal asymptote, I want you to go ahead and find our x-intercept and our y-intercept. So go ahead and pause. All right, so from our x-intercepts come from factors in the numerator. The only factor we have in the numerator is that x plus 2. So we set x plus 2 equal to 0, which gives us negative 2 comma 0 for our x-intercept. For our y-intercept, we would plug in 0. So 2 times 0 plus 2 over 0 minus 3. That would simplify down to positive 4 over negative 3. So we get the y-intercept of 0 comma negative 4/3. One important note, that 2 that's up there in the top, it is not a factor. So I'm not going to get like a second or x-intercept of there. For something to be a factor, it has to involve x. So that 2 that we took out as a GCF, it's not going to produce a second x-intercept or anything like that. Okay. So go ahead and finish this one out by finding if there is a hole and then denoting the domain and range of our function. So go ahead and pause me one last time. All right, y'all. And we did not have any factors cancel when we did our simplifying. We reduced some GCFs, but we did not cancel out any factors. So our hole in this case would be none. And then for our domain, the only thing that we're excluding from the domain is that vertical asymptote of x equals 3. So our domain is negative infinity to 3 in union with 3 to infinity. And our range, only thing we're excluding is that horizontal asymptote. So we're going from negative infinity to 2 in union with 2 to infinity. Okay, now that we've found all of our key features, hopefully you got some practice doing it on your own. Let's go ahead and graph this one. So our vertical asymptote was at x equals 3. Our horizontal asymptote was at y equals 2. So vertical asymptote at x equals 3. Horizontal asymptote at y equals 2. And then our x-intercept and y-intercept, our x-intercept was at negative 2 comma 0. And our y-intercept was at 0 comma negative 4/3. So that's going to give us one of our two curves, which is going to be down here in our bottom left. Okay. And if our rational function stays true to the way they should look, we should have one that is symmetrical and up in that top right box. But if we wanted to check, if we wanted to be totally sure, we can just pick a number just to the right of that vertical asymptote to plug in. So in this case, let's plug in 4. So if we did f of 4, we would get 2 parentheses 4 plus 2 over 4 minus 3, which is equal to 4 plus 2 is 6. 6 times 2 is 12. So 12, not 16. 12 over 1, which would just be equal to 12. And 12 is going to be off our graph a little bit, but that 12 is definitely higher than our horizontal asymptote of 2. So I know that we're going to be up here to the top right. So we'd have that second rational curve up there in the top right. Okay. And like I said, y'all, in general, we do have that symmetrical shape to our rational functions, but every once in a while, it will not hold true. So it is important to always make sure we do that check for that last piece. Okay, so we did B, we did C. Let's go ahead and look at D. So D, we got a lot going on. We have 4x squared plus 4x minus 24 over x squared plus x minus 20. Okay, so in this one, we definitely look like we're going to have some things maybe cancel out if we do some factoring. So we want to go ahead and factor this one right off the bat. Okay, so first and foremost, that 4x squared plus 4x minus 24, I always want to make my factoring as easy as possible. So for this one, I'm going to go ahead and take out a GCF of 4 of all 3 of my terms. So that would give me 4x squared plus x minus 6. Then in the bottom, x squared plus x minus 20. So I need factors of negative 20 that add up to positive 1. So that would be positive 5 and negative 4. So that's going to factor into x plus 5 and x minus 4. Okay. And then on top, that 4 times x squared plus x minus 6, that 4 is already out, but that x squared plus x minus 6, that would, I'm looking for factors of negative 6 that add up to positive 1. That would be positive 3 and negative 2. So this will fully factor into 4, x plus 3, x minus 2, all over x plus 5, and x minus 4. All right, and now that I have fully factored the top and the bottom, I'm not going to get any factors to cancel out, so that is my fully simplified rational function. Okay, now we've done a couple, y'all, where we found all of the different key features, so I want to see if you can do this one completely on your own. So go ahead and pause me here for just a second, and you're going to be finding all of our key features from vertical asymptote all the way down to the domain and the range. For the domain and range, I would recommend that you write those in set notation, are all real numbers except x or y does not equal. It's going to be a little bit easier than doing 3 intervals. So go ahead and pause and find those key features. All right, y'all. So these key features for our vertical asymptote, because we have those 2 factors in the denominator, we do end up getting x equals 4 and x equals negative 5. For our horizontal asymptote, we do have x squared over x squared, but it's 4x squared over 1x squared. So its exponents are the same. We're going to divide those coefficients. So 4 divided by 1 would give us y equals 4 as our horizontal asymptote. For our x-intercepts, because we have 2 factors in the numerator, we're going to end up getting 2 x-intercepts, negative 3 comma 0 and 2 comma 0. For our y-intercept, we plug in 0 across the whole thing. So 4 times 0 plus 3 times 0 minus 2 over 0 plus 5 times 0 minus 4. So on top, that would reduce down to 4 times negative 6 over negative 20 on the bottom, and then negative 24 over negative 20, which we can simplify down to positive 6/5. So 0 comma 6/5 for our y-intercept. For our whole, we once again did not have a factor cancel out, so we do not have a whole. So our whole is just none. And then for our domain, like I said, I recommend you write it in set notation. And the reason why is because we have multiple things we're excluding. if we did interval notation, we'd have to do at least 3 separate intervals, which can get kind of gross. So all real numbers except x does not equal those two vertical asymptotes, -5 and 4. And then for our range, all real numbers except y does not equal that horizontal asymptote, which is y equals 4. Okay, let's use all these key features to go ahead and actually graph this function. So let's look. Our vertical asymptotes were at -5 and +4. So let's go ahead and add those on. And then our horizontal asymptote, and that is a terrible vertical asymptote, but our horizontal asymptote was at 4. Okay, and then our two x-intercepts were at -3 and +2. And our y-intercept was at 0.6, which is a little bit above 1. Okay, and you might notice a couple things. So first and foremost, we're now having these 6 separate sections formed for our rational functions instead of the 4 we've been dealing with. So anytime you have those multiple vertical asymptotes, you're going to get this 6 sections instead of the 4. And it's just going to make it a slightly more complicated rational function. Okay, but just like we did before, we're going to plot our points, do our asymptotes, and then we'll kind of start working with our curves from there. So if you notice, we have these 3 points down here at the bottom. It's actually going to end up creating this kind of quadratic shape down here in that middle section. Hopefully that's a little familiar from what we saw in that Desmos activity. You might have seen a couple that kind of look like this. Okay, now, as we've talked about before with our rational functions, y'all, if we've done everything correctly, and if this is kind of a normal rational function, it should be symmetrical. So see how we have this quadratic function down here in the bottom of this middle section? We should have a rational curve up in the top right square and up in the top left square. But it's not good to assume. So to check, we can do our same plugin. We're just going to have to do 2 numbers plugged in instead of just 1 this time. So we're going to plug in f of -6, because that's just to the left of my vertical asymptote, and f of 4, because that is just to the, or not 4, sorry, 4 is my vertical asymptote. 4 would give me undefined. I want to plug in f of 5. Okay, so go ahead and plug both of those in for me. I'm going to let you do it on your own this time when you plug in those numbers into our function. And you can plug it into the original or to the simplified, whichever one you want. If the number is higher or above the horizontal asymptote of 4, then you're going to graph those rational functions above. If it is lower than 4, then you're going to graph them below. All right, and as you can see, y'all, when we plug those values in, we actually end up getting the exact same y value for both, which is 96/10. So that 96/10 is about 9.6, which is definitely higher than our horizontal asymptote of 4. So we're going to get those 2 rational function curves up in the top right. Okay, so a little bit different, but anytime we have those vertical asymptotes, we're going to get this kind of slightly different shape in the middle. And this one ended up being that quadratic shape. You can also get a cubic shape that forms in the middle. So you can get kind of some wonky things with some rational functions. Just make sure you find all of those key features. And then if you don't know exactly what the shape of the curve is, to get more points, we can plug in just to the left and just to the right of a vertical asymptote. That always works. It takes some time, like this one. I mean, those are some pretty gross fractions that we just had to plug into. So it's definitely going to take some time to graph something like this. But the time is worth it, A. And B, you can plug in as many points as you need to feel comfortable and confident with the shape of the rational function. Okay, let's look at one that's going to be just a little bit different. Let's look at graph E. So we have x squared plus x minus 2 over x squared minus 5x plus 4. Okay. So just like we did for D, we are going to factor this one. So x squared plus x minus 2 over x squared minus 5x plus 4. So first and foremost, we want to factor the top. So factors of negative 2 that add up to positive 1. That would be x plus 2 and x minus 1. And on the bottom, we have x squared minus 5x plus 4. So factors of positive 4 that add up to negative 5. That would be x minus 4 and x minus 1. Okay. And hopefully, as we were doing this, maybe you had a little bit light bulb go off, because now we have that x minus 1 over x minus 1. And that is going to cancel out for us. Okay. And it's going to leave just x plus 2 over x minus 4. So after we've factored that, we now end up with this significantly more simplified rational function. This x plus 2 over x minus 4 is very similar to our rational function on A, x minus 2 over x plus 5. But because we got that factor to cancel out, hopefully you've now recognized we're going to end up with a hole on this one. So we haven't had that procedure yet, but we'll talk about what that looks like when we get to our hole. Okay, but first and foremost, for our vertical asymptote, we only have one factor in the numerator, which is that x plus 2. So our vertical asymptote would be x equals negative 2, because it's always set equal to 0. Okay, our horizontal asymptote, this is an exponents are the same, because it's x squared over x squared. And so because our exponents are the same, we're going to divide those coefficients. Oh, no. Did it just delete my whole video? We're back. Okay, so because those exponents are the same, we're going to divide those coefficients. So 1 over 1 would give us y is equal to 1. Oh, and slight correction, y'all, because I realize I'm being crazy. Our vertical asymptotes come from factors in the denominator, so this should be x equals positive 4, not x equals negative 2. But our x-intercept is going to be negative 2 comma 0, because that comes from factors in the numerator. Okay, then our y-intercept, we would plug in 0, so 0 plus 2 over 0 minus 4 would give us 2 over negative 4, or negative 1/2. Okay, and then our hole, which we've usually been saying none, this time we do actually have a hole. So that x minus 1 and that x minus 1 cancels out, which means we have a value of our hole at 1. Okay, it has an x value of 1. We take that x minus 1 and we set it equal to 0. And we get x is equal to 1. So then we're going to take that 1 and we're going to plug it in to our simplified function. So 1 plus 2 over 1 minus 4, which gives us 3 over negative 3, which then gives us negative 1. So our value for our hole is 1 comma negative 1. So the x value for the hole comes from the canceled out factor set equal to 0, and the y value from the hole comes from taking that x value and plugging it back into the function. And then last but not least, y'all, for our domain, we exclude any of those x values, so any vertical asymptotes, in this case are 4. Okay, and then any x values of a hole, which we haven't had before, but this time we do. So that 1. Okay, and then for our range, we exclude any horizontal asymptotes, so all real numbers. Y does not equal 1. And any y values of the hole, because that would also be an undefined spot. So does not equal -1. Okay, so now that we have found all of our key features, we have everything mapped out, we can go ahead and add in our graph. So just like we've been doing before, we do horizontal and vertical asymptotes first. So vertical asymptote at x equals 4, horizontal asymptote at y equals 1, x-intercept at -2, 0, y-intercept at 0, -1/2, and whole at 1, -1. Okay, so I have all those things down in this bottom left section, so I am definitely going to have a rational curve down below. Okay, and if everything is correct, I should have that curve in the top right, but it is always good to check. So let's just check f of 5 really quickly. So f of 5 would be 5 plus 2 over 5 minus 4, which would equal 7 over 1, which is 7. So we'd get that point 5, 7, which definitely puts our rational function where we thought it should be, up there in the top right. Okay, so the only extra thing when we do that whole is A, we do get that canceling out, which gives us a simpler rational function to work with. And then B, we find that whole by plugging in, setting that factor equal to 0 to find x, and then plugging that x back in to get y. And then, of course, we get that open hole on our graph. Everything else is exactly the same. Okay, we don't have a lot of time. This video is already pretty long. So let's do just one more question. And I'm going to let you do this one mostly on your own. So we're going to be looking at f. So f of x, we have 3x squared minus 9x minus 30 over x squared minus x minus 20. Okay, so first and foremost, go ahead and pause me and see if you can factor this one on your own. All right, y'all. So hopefully you took that 3 out on top. So we got 3 times x squared minus 3x minus 10 over x minus 5 times x plus 4. Then on top, that x squared minus 3x minus 10 does factor into x minus 5 and x plus 2. Those x minus 5s are going to cancel out. So we get the simplified fraction of 3 times x plus 2 over x plus 4. Okay, so now that we should all have the same function, I want you to use that function. 3 times x plus 2 over x plus 4 to go ahead and find all of our key features for this one. All right, y'all. So in our numerator, or on our denominator, we only have the factor x plus 4 left over. So that's going to give us the vertical asymptote of x equals -4. For our horizontal asymptote, exponents are the same. So 3x squared over x squared is going to give us the horizontal asymptote y equals 3. For our x-intercept, we only have the one factor x plus 2 left in the top, so that's going to give us an x-intercept of -2. For our y-intercept, we're going to plug in 0 and 0, so 3 times 0 plus 2 over 0 plus 4 would give us 6/4, which would reduce down to 3/2. Then for our whole, the factor that canceled out was that x minus 5, so that's going to give us x equals 5, and then we plug 5 in. 5 plus 2 is 7, times 3 is 21, over 5 plus 4 is 9, and 21/9 can be reduced down to 7/3, so we get 5, 7/3. And then, of course, for our domain, we have all real numbers except x does not equal -4 and 5. And for our range, we have all real numbers except y does not equal 3 and 7/3. Okay. So now that we have all of our key features, I'm going to see if you can graph this one on your own as well. So go ahead, and you maybe got a little bit of a sneak peek over there on the side, but go ahead and pause me and graph this one. All right, also seeing everything together, we have that vertical asymptote at x equals -4, a horizontal asymptote at y equals 3. Our x-intercept, y-intercept, and whole all plot in that bottom right, which gives us that nice little curve. So since we did not have any points over in the left, to graph that one, we just plugged in f of -5. Plugging in f of -5, we would get 9. So -5 comma 9 gives us a point up there in the top left, and we have that nice little standard rational shape. Okay, so I've left 2 for you to complete on your own. We did not do B, so you can go back and do B. It's a little weird, so I'll warn you. And then E, F, G should be just below. Let me check. Yeah, G is just below. So you can do B and G on your own and see how you're doing. The key is already posted on Canvas, so you can check your work on Canvas. For some practice on this, y'all, we have that rationals matching activity as well as your rationals practice. And of course, once you're feeling confident, don't forget to take that 4A.1 through 4A.2 graphing rational functions exit ticket. All right, y'all, that's all I got. Come in for tutorials if you have any more questions.